Okay, good morning. We have William H. Murray on the line. And Bill, go ahead, take it away with the cost of the attack.
Many security experts behave as though all vulnerabilities are equal and that all attacks are free. Indeed, vulnerability pimps are defined by this belief. After all, they do not have to pay the graduate students who do the work or even pay for their computers. This is complicated by the fact that script kiddies who cannot sell their labor think that it has no value. Like many of the abstractions that we use in security, the cost of attack cannot be calculated with any precision. However, it can be modeled in a useful way, in a way that enables us to compare it to the value of success, in a way that enables us to make better security decisions, in a way that enables us to understand how to reduce the probability of a successful attack. The first component of the cost of attack is work. Some person or some computer will have to do work that can be measured in man-hours or computer cycles. Someone must do analysis, identify both a class and an instance of a vulnerability, design an attack, identify targets, or write and test programs. While the cost of skilled labor rises over time, this may be offset by the falling cost of computer time. The upper bound on the work required for the attack is that required for a brute force attack. We cannot always know the lower bound because we don't know the cost of resources to the attacker. Second, after work, the attacker must have access to the target. At a minimum, she must be able to send a message to the target system. In the early days of computers, when few were connected to the public networks, most of those who could connect or send a message were insiders. They were defined as insiders by this privilege. Most of these were authorized users, people who were intended to use the system or the application. In the modern world, in which most systems or applications are attached to public networks, almost anyone can send a message to almost any address, not to say any system or application. Said another way, most of those who can send a message to a system today are not authorized users. Third, the attacker must be relatively indifferent to detection. This indifference is scarce and can be modeled as a cost. Note that some potential attackers are much more indifferent than others. The guy in Russia is not so worried about being caught in an attack against the US. Somebody in China may not be quite so concerned about being caught in an attack against the US. The less likely that an attacker believes that he is to be identified and penalized, the lower his cost of attack. Fourth is special knowledge. The attack may require significant special knowledge. It's interesting that those who have the most special knowledge tend to discount its value. For example, the infamous graduate student who spent most time and treasure obtaining knowledge assumes that it is plentiful and cheap, that if he knows something, everyone knows it. However, in fact, the more knowledge that is required for the success of an attack, the fewer people there will be that can succeed at it. Finally, there's time to detection and corrective action. The greater the time required for an attack to succeed, the greater the potential that it will be detected and thwarted in progress. Indeed, we detect and thwart most attacks in progress. Many so-called experts talk in terms of attacks that are never discovered. The time to the discovery of an attack is a function of its success. That is, the pain to the victim and the benefit to the attacker. Now, for these 5 things, I use the acronym WASTE, W-A-I-S-T, to teach and remember the variables in the model: work, access, indifference to detection, special knowledge, and time to corrective action. Notice that any of these factors can be purchased for dollars. That is to say, can be priced in dollars and compared to one another. Said another way, they are fungible. An excess of one may reduce the amount of any of the others that will be required. For example, if one has knowledge of a password or a key, one might avoid the work that would otherwise be required to discover it. Both work and special knowledge can be encapsulated in a computer program, made available to those without the knowledge and unwilling to do the work. This is what makes script kiddies such a nuisance, not to say a menace. One can use this model to understand how to increase security, that is, how to reduce the probability of an attack by increasing its cost. Said another way, we can use the model to compare the cost of attack to the value of success. Note that we define a hardened target as one where the cost of attack is greater than the value of success. This implies that we were able to model both the cost of attack and the value of success. While one cannot guarantee that even a hardened target cannot be successfully attacked, we can be sure that no one will do it over and over again just for the money. As with other abstractions, like risk, we are called security professionals and paid the big bucks because we understand and use abstractions like the cost of attack. See you next week. Next week I'll be back home in Connecticut.
Thanks, Bill.